Okay, page 3. 11, write a Maclaurin series for e to the 3x. So we're going to be following something similar that was done in question 10. And I do have e to the x written up here. So if I were to write e to the 3x, that's a composition. It's like I'm going to plug in 3x into every x spot that's given here. So that'd be 1 plus 3x plus 3x squared over 2 factorial plus 3x to the third over 3 factorial plus 3x to the fourth over 4 factorial, so on and so forth. And there you go. If we want to write the general term for this is x to the n over n factorial, so you can write it as 3x to the n over n factorial for the general term. Okay, write a power series of e to the x plus e to the negative x. Well, so I already have e to the x written here. So what is e to the negative x going to look like? So e to the negative x will look like if you're going to substitute in negative x. So that's not going to change the first term. That will change the next term to be negative x. But if I plug in negative x here, that's still going to remain positive x squared. And this is still going to remain positive x to the fourth. Odd terms are the ones that are going to turn negative. So plus x squared over 2 factorial minus x to the 3 over 3 factorial plus x to the fourth over 4 factorial, so on and so forth. So if I were to add e to the x and e to the negative x, so think about it like I'm adding these two together. Well, if I add them together, I get 1 and 1. That's going to give me 2, right? So I'll say e to the x plus e to the negative x is going to be equal to 2. If I add the next terms together, those are going to cancel. These are going to cancel too, right here. This right here is going to double because I have 2 of them. So plus 2 x squared over 2 factorial plus 2 x to the fourth over 4 factorial plus 2 x to the 6 over 6 factorial, so on and so forth. But then if I divide by 2, divide all this by 2, this becomes 1. Those cancel right here, so on and so forth. So e to the x plus e to the negative x over 2 will be equal to 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial plus x to the 6 over 6 factorial, so on and so forth. Yeah, I would just leave it like that. Okay. 13. So we're going to let f be a function having all derivatives of all orders for x is greater than 0, such that f of 3 is equal to 2, f prime of 3 is equal to negative 1, f double prime of 3 is equal to 6, and triple prime of 3 is equal to 12. Write the third degree Taylor polynomial for f about x equals 3. So as a quick reminder to what a Taylor polynomial is, so a Taylor polynomial can be written as such. N equals 0, it's the nth derivative at the center over n factorial times by x to the that is a poor choice of terminology. X minus c. Sorry, I probably misspoke too. This is not at the center. We're just going to say at some value of a. Okay? C is the center. A is where you're evaluating it at. So write a third degree Taylor polynomial for f about x equals 3. In this case, it looks like, oh man, that's kind of confusing for this problem. So we're evaluating the derivatives at, at the center. No, I think I was right. At the center. At C, x minus a. I can't remember. I gotta go look at the definition. I don't think it matters though. But in any case, it's centered at 3 right here. So usually in these type of problems, if it says a Maclaurin series, it's centered at 0. If it's calling it a Taylor polynomial or a Taylor series, make sure that you're paying attention as to where it's telling you that it's where it's being centered at. So it's going to be 3 right here. So in any case, right here, we're pretty much all this information given here, f of 3 of 2, f prime 3 of negative 1, f double prime 3, all this right here, it's pretty much giving us all of this information right here for each term that we have. So the 0th derivative is 2. The first derivative at where we're looking at is negative 1. So on and so forth. So in this case right here, my third degree Taylor polynomial, sorry, I hope you guys don't, I'll keep it there. I was going to erase it, but so my third degree Taylor polynomial here, let's start by writing, well, the zeroth the zeroth derivative at 3, which is 2. So I would say 2 divided by 0 factorial, but 0 factorial is just going to be 1, times by x minus 3, because that's where it's centered at, to the 0th power, but all of this is just going to be 1. So this is the first term of my Taylor polynomial. Okay, then, well, what's the first derivative at 3? Negative 1, so I know this is going to be subtraction, over 1 factorial, so this is going to be over 1 factorial, which is just 1, times by x minus 3 to the first power. So I'm just going to say x minus 3. And we just keep building. So then it's going to be plus 6 over 2 factorial. Well, 6 over 2 factorial is just going to be 3. Okay, times by x minus 3 squared. And we want a third degree Taylor polynomial, so go one more. So I'll say plus 12 over 3 factorial. 3 factorial is 6, so 12 divided by 6, that's going to be 2, times by x minus 3, oops, sorry, that needs to have an nth power, to the third, and there you go. So this right here would be the third degree Taylor polynomial. So it's kind of nice here. I'm not asking you to, so I'm not giving you a function of f of x where you have to find the first 3 derivatives of them and then plug in the value that it's asking for. It's just giving all of that to you. So that's very nice. I'm probably going to keep that a problem like that on the test where you don't actually have to find the derivatives. You just have to plug in the values that are given to you. Okay? And there you go. There's your Taylor polynomial. So again, remember the difference between a Maclaurin series and a Maclaurin polynomial and a Taylor polynomial. If this were a Maclaurin polynomial, these would just be x. So x to the first, x squared, x to the third. Remember that if it's asking for a Taylor polynomial, it's likely to give you a center where you have to do x plus or minus whatever value it's centered at, right? Okay. 14. If the infinite series, so here's the series here, is approximated by p sub k, that's polynomial notation. So basically it's saying that you're going to have a polynomial with k terms that's going to be truncated. What is the least value of k? So k is the number of terms. So for how many terms do you need? So which value of k for which the alternating series error bound guarantees this right here. So we're using the alternating series error bound. So what's the least number of terms needed to guarantee that your error is going to be less than 3/100ths? So so here's the thing. S is given here. P sub k is given here. This error bound has to be a sub n plus 1. It has to be the nth plus 1. This is the first omitted term. So we are going to the term p sub k, right? So we're going to, well, I guess I can write like this. So p sub k will be equal to a sub 1, a sub 2, plus a sub 3, plus a sub 4. I guess I should write this as alternating dot 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 all the way to a sub n. We're going to truncate it right here. So this right here is, all this right here is p sub k, which is right here, which means the nth plus 1 term we want to be less than this right here. So what is my nth plus 1 term? Well, I'm just going to plug in n plus 1 into, I guess, either one of these. Doesn't really matter. So a sub n plus 1 has to be less than, well, has to be equal to, I guess, in this case, the absolute value of negative 1 to the n plus 2 times by 2 over n plus 1. So I'm basically just using these descriptors of my nth term right here, and I'm plugging in n plus 1 for n to get my nth plus 1 term. Since it's the absolute value, that part doesn't matter. So nth plus 1 is going to be equal to 2 over n plus 1, and I want this right here to be less than or equal to 3 100ths. Okay, so I'm just going to treat it as if it were an equal sign. Okay, well, doing some algebra here, you can do a cross multiplication. So you get 3n plus 3 when I multiply these together is equal to 200. I can subtract 3. So I get 3n is going to be equal to 197. I can divide by 3, and I'll get n is equal to, so 197 divided by 3, which is equal to 65.667. So this right here is n or k, however you want to look at it, is referring to what we're looking for. So we set it up where we're basically solving for the number of terms that I need to get this error right here, right? So I have to be, since we're going to be rounding to whole numbers right here, I'm going to want to have the least value of k. So I'm going to go down to 66. That's the least value it could be. So when k is equal to 66, we're basically saying that this series needs 66 terms in order for my error to be less than 3 100ths. So there you go. Okay, so for a function of f, the fourth degree Taylor polynomial about x equals 0 is used to approximate f of 0.1. So it's not really being specific about what the function is. It's just saying for a function of f, the fourth degree Taylor polynomial about x equals 0 is used to approximate this. So there's a Taylor polynomial. We have f of x, and this f of x is equal to some sort of series, some power series right here, and this series can build out a polynomial, and we're going up to the fourth term of this Taylor polynomial. Okay, and we're going to plug in 0.1 for x to approximate all of this right here. So we're using the Taylor polynomial to approximate f of 0.1. Okay, given that the fifth derivative, the absolute value of the fifth derivative of my function, the most it can be is 15 over the interval from 0 to 0.5, use the Lagrange error bound to show that this approximation is within 1 over 10 to the fifth of the exact value of 0.1. So the Lagrange error bound says that the error, so this is for non-alternating series, right? So honestly, it could be used for alternating series too. But the error has to be less than or equal to the max value of the absolute value of my nth plus 1 derivative at some value of z times by x to the nth plus 1 over n plus 1 um, over n plus 1. N plus 1 factorial, because we're using a Taylor polynomial. So this right here is what we're looking to use. We're looking to find out what the error bound is. Okay, we're still pretty much basing a lot of it is very similar to the alternating series error bound, where we're looking to use the first omitted term. So if we're using the fourth degree Taylor polynomial to approximate f of 0.1, the first omitted term would be the fifth degree. So which is why they gave us all this right here. So the maximum right here, the maximum value of my fifth derivative at some value of z, they're telling me this part. It's 15. The most it can be is 15. Okay? Times by, well, this is going to be x to the fifth over 5 factorial. So this right here is the most my fifth term is going to be, and my error has to be less than that. Okay? And we're approximating 0.1, which is the same thing as 1/10, so I'm going to plug that into my error formula. So 1/10 or 0.1 to the fifth over 5 factorial. Well, this right here is 5 times 4 times 3 times 2 times by 1. These terms right here multiply to be 15. These terms multiply to be 8. So this will cancel with the terms of 5 and 3. I'm also going to put that 10 to the fifth in the denominator here, times by 8. So again, if you didn't catch that, 5 factorial is 5 times 4 times 3 times 2 times 1. 5 times 3 is 15, so that's going to cancel with that 15 in the numerator. This is going to be 8 right here. 1 over 10 to the fifth is the same thing as 10 to the fifth in the denominator. Now this obviously is less than 1 over 10 to the fifth, because you're also multiplying the denominator by 8. There you go. So use the Lagrange error bound to show that this approximation is within 1 over 10 to the fifth. There you go. So it's actually not too bad of a problem. Just remember that this value right here is almost always given to you. It's gonna have to be given to you. We kind of talked about it in there's a if you look back in the notes, this right here has to be given to you, because we don't know what value z is. We don't know the maximum value we're gonna get here. So yeah, this value has to be given to you. Plug in your value of x and evaluate. Okay, let's stop this video right here.